Okay. So we ended yesterday. We were looking at the Taylor series for ArcSign. It ended up being a little messy. I was taking a look at that afterwards, and there's easier ways to write it. Though they involve some fancy tricks involving factorials. So we tried to practice factorials as much as we could, but unfortunately, being summer, we didn't have a whole lot of time to do it. Um, I'm going to leave it as it is. Let me know if you guys want to see how we can modify it a little bit better. We didn't end up with a nice and concise closed form expression for it. There's ways to get around it, and there's a trick namely involved what we were seeing in the numerators, in the coefficients in the numerators. We were seeing a consecutive product of odd terms. So you can deduce that, or you can notate that with just normal factorials if you're really clever. In general, if you have like a linear series and a product of consecutive linear terms, you need new notation. You need like this, what's called pi notation for products. But with something that's only either even or odd terms, you can write it with factorials. It's a little tricky, a little technical. So maybe I'll show you guys that either in office hours, if you guys are curious. The Taylor series for ArcSign, though, it's not something you should be forced to memorize. It is a fairly tricky one. I think in general, if you can arrive at writing out the consecutive terms. So here, let's bring up the page. So we ended with something like this. If you can get to something like this and show that you can derive all of the consecutive terms, especially for a function that is going to be as complicated as ArcSign, coming up with a closed form expression from this starts to get a little advanced. And of course, as we saw, it's kind of hard to write these consecutive products. So maybe if we have time, we'll go back and readdress that. For now, I want to move on and want to make sure we cover the remaining topics. Namely, we want to talk about products and quotients of Power series and Taylor series. Those are going to come. It's going to be fairly quick. It's it's not fun. It's a lot of computation. So we'll try to go through at least two examples, either the x sine x for a product, and then trying to come up with a Taylor series for tangent, looking at the quotient of sine and cosine. The quotient is going to be, it's a lot of computation. And again, it's going to be one of those things where we want to compute maybe the first three terms or something. A lot of the problems in the book, and I would imagine the problems on WebAssign are similar, where if you have to compute a product or a quotient of Taylor series, computing the first three or four terms is usually enough work. And if you can then deduce a closed form expression from the pattern you see in the first three or four terms, that's usually enough of a guess. It's not a rigorous mathematical proof that that is what the Taylor series is, but at this level, it's good enough. The other thing we want to talk about, limits of Taylor series, and then we also have to get into remainders and errors of Taylor series. So let's talk about limits with Taylor series first. It's fairly easy. I think it'll be an easy topic to warm up with before jumping into some more harder calculations with these products and quotients. So let's suppose we want to compute a certain limit. And let's start off with this one. Sine of x over x. I think that we saw this limit earlier this year, or at least we saw a series like sine n over n or sine n over n squared or something to that effect. And so working with functions like sine and cosine, right now our techniques, we often bound them whenever we're working with those in terms of sequences and series. The other thing we can do now that we actually know Taylor series for sine and cosine, we can approximate sine and cosine to however many orders. So of course, this is going to give us a fairly easy L'Hopital's 0 over 0. And we could take derivatives and then find the limit from that. The other thing we could do is note that our sine of x, since it has a nice Taylor series, we notice that, so sine was an alternating series of the odd powers of x with an odd factorial. So if we were to write it out, it's going to be x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and it's going to keep going. And so when we want to compute a limit, now we can replace functions with their Taylor series, as long as the limit we're computing is, of course, within the radius of convergence. So sine of x, we know, converged for all x from minus infinity to infinity. So we don't have to worry too much about that. And so if we look at the Taylor series limit, you do want to be careful about the starting values of the indices, and you can get around some of the errors that will occur, especially if there's a constant term, by simply writing it out. So we know that we want the limit going to 0 of x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. And then we can write the 1 over x as a product on the outside. And of course, when we distribute that, it'll just simplify all the numerators and bring out 1 power of x. And now what's going to happen when we plug in x equals 0? All of the terms with an x still in it are going to vanish. And so our limit is just 1. So we can use this method for any sort of functions now that come up. And usually, nicely enough, if our limit is going to the base point of the series, so if our series is centered at 0, we like it when that happens. Computing, using those in limits in that situation, it's going to be nice because usually all of the higher order terms are going to vanish. And so really what we're looking at is the lower order approximation for the function. So for example, if we want to compute the limit as x goes to 0, 1 minus cosine x over 1 plus x minus e to the minus x, e to the positive x, We can do the same process by simply replacing all of the non-polynomials with their Taylor series. So cosine x will be the even terms. And then in the denominator, we've got e to the x. There's no multiplication going on between those series, but if we were to write out the first few terms of each of those sequences, of each of those series, what do we get? So we're going to have 1 minus. So cosine now, when n starts at 0, is going to start at 1. Second term is going to be x squared over 2 plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. Divided by 1 plus x minus, let's go ahead and write out e to the x, 1 plus x over 2, x squared over 2, plus x cubed over 3 factorial. And now the algebraic simplifications we need to make are to just simplify, distribute our minus signs, and then simplify any of these extra polynomial terms that were appearing outside of these sequences. So when we distribute this minus sign, of course, all the minus signs are going to flip. 1 minus 1 will cancel each other out. And then likewise here, everything will be negative, and the 1 and x will cancel out of the first couple of terms there. And so what are we left with? Left with the limit as x goes to 0 of, we'll have x squared over 2 minus x to the 4th over 4 factorial plus x to the 6th over 6 factorial minus, and that'll keep going. Then in the denominator, since the 1 and the x will cancel, we will start with minus x squared over 2 minus x cubed over 3 minus x to the 4th over 4 factorial. Maybe we want to write some extra terms. Let's write one more, both on the top and bottom. I always like to write out and have at least 4 terms. It makes the patterns easier to see. So now how do we compute this limit? In this case, we're still getting a 0 over 0. But we kind of want to treat it in some sense like our polynomials. If we had a finite polynomial, we would compare the highest powers. Unfortunately, since we have infinite polynomials, the powers are going to keep increasing and increasing. So in some sense, what we're going to do is just use tricks at the lower order terms, especially since our limit is going to 0. So what you want to do is just factor out that lowest order term. And let's see, so I'm just trying to think of what to do with this constant. I think we want to just leave these constants here. We can factor out a 2 from each of these terms. We can factor out a 2 from each of the denominators here as well. but then it's just going to be harder to write because then it'll be weird factorials. We could. I don't know if it would quite help us. But it'll be easy enough to simply pull out the highest powers of x. So if I pull out an x squared, or excuse me, the lowest powers of x, pull out an x squared from the numerator, we're going to have 1 over 2 minus x squared over 4 factorial plus x to the 4th over 6 factorial minus x to the 6 over 6 factorial. Did I miss one? Yeah, wait a minute. Get him in number script over 8 factorial. Pull out an x squared here, and if we want, we can pull out a negative x squared. So that'll give us 1/2 plus x over 3 factorial plus x squared over 4 factorial plus x cubed over 5 factorial. And then, of course, our x's cancel. And now what are we left with? Mind this minus sign still in the denominator. When we plug in our limit for x now, the zeros are going to kill all the higher order terms. And we're going to be left with 1/2 over negative 1/2. And so our limit is -1. Any questions on those? So those, I mean, once you get the hang of Taylor series, it looks like a little bit more work, but it's actually like once you get the hang of it and can not have to write out too many of the higher order terms, the manipulations can go pretty quickly. Whereas if you look at the original problem, especially once cosines and e to the x's come up, they are cyclical in terms of their derivatives. So if we have to do L'Hopital's rule with stuff like this, occasionally we run into problems where we either have to do L'Hopital's rule multiple times, or L'Hopital's rule won't even work. We can keep doing L'Hopital's rule over and over again and get stuck in this L'Hopital's rule loop and never be able to find an answer. So anytime you're getting in one of these loops of L'Hopital's rule limits, really what you want to do is some sort of algebraic manipulation. And now we essentially have a new tool with our power series. We can just algebraically manipulate the power series for functions and use those in computing limits. Okay, let's take a look at products and quotients. And the best way to do this is just to start taking a look at examples. It's all computational. So if we have a function, e to the x cosine of x, and if we want to come up with a power series or a Taylor series for this guy, it's going to be difficult. So if we were to go through the process of computing the Taylor series, following the formula, what do we need to do? We need to compute consecutive derivatives, f prime, f double prime, f triple prime, and keep going. But what's the problem with that? Even computing the first derivative isn't terribly nice because we have a product rule. And as soon as we have a product rule, well, now my first derivative is going to have two terms, right? It's going to split into a sum of two different products. Moreover, our derivatives of e to the x and cosine x, they're never going to vanish. They're going to keep cycling. So not only will I have a sum of two products, but then when I take a derivative of that, nothing's vanishing. Then I'm going to get potentially a sum of four products and my second derivative. And then it's going to keep growing and growing. The number of terms is just going to get out of control. And it's going to be hard to compute more than 3 derivatives. Let alone, then we have to evaluate that. So sometimes if the derivatives start with this cyclic nature start to develop some patterns, even within product rules, sometimes you can deduce formulas once we evaluate it as well. Some of the terms are going to vanish, especially if we're centered at 0. So maybe we should specify at x equals 0. But now the other thing we can try is, since we know the Taylor series for both e to the x and cosine x centered at x equals 0, we can try to compute their product. And I mentioned earlier, when we were first starting Taylor series, that we don't want to do this. And in general, if you can avoid it, you'll see why we want to avoid it. Some addition and scalar multiplication of power series works very nicely if they're convergent. But as soon as we get in the products, we've got to develop a better mathematical algorithm. And there really isn't a nice way to do it other than it's like plug and chug. It's basically multiplying, polynomial multiplication, except we have an infinite degree on both polynomials. So writing it out in terms of their sigma notation, not going to work too well. We are actually going to have to write it out in terms of an expanded form, an expanded sum. So let's go ahead and write out e to the x. We have 1 plus x squared over 2 plus x cubed over 3 factorial plus x to the 4 over 4 factorial. Let's write out 5 terms there. And if we need more in consecutive steps, we can write out more. And the way I'm going to multiply them is like you would multiply like large numbers. So if you think way back in elementary school, when you learn to multiply a 3-digit number times a 4-digit number, we're going to use essentially that algorithm. So instead of listing them next to each other, it's going to be easy enough to list them on top of each other with the corresponding powers of x considered as our digits, as our placeholders for those digits. So cosine is going to be 1 minus x squared over 2 plus x to the 4th over 4 factorial. And we can write a minus x to the 6th over 6 factorial. We might have to include some more terms there. So we're going to put them on top of each other. I don't want to use x again, so I'm just going to put a dot there for times. And what you can do is now start with this 1, multiply by the entire sequence, by the entire series. Then use this minus x squared over 2, multiply out the entire sequence. And slowly what we'll see is we'll start to develop a pattern for the lower order terms, and the more products we take, we'll get patterns for the higher order terms. So let's see what we can get. And actually, you know what? Let's go ahead and get a new piece of paper and rewrite this. So we've got 1 plus x squared over 2, x cubed over 3, x to the 4th over 4. Let's actually include more now since we got space. X to the 5 over 5, x to the 6 over 6. It's our e to the x, and then we are multiplying by 1 minus x squared over 2 plus x to the 4th over 4 minus x to the 6th over 6 factorial. And that is our cosine. We're taking a product, and then when I multiply everything times 1, we're going to get that exact same sequence. So we will have, let me spread things out a little bit, 1 plus x squared over 2 plus x3 over 3 factorial, x to the 4th over 4, x to the 5th over 5, x to the 6th over 6 factorial. That was multiplying the 1 through. What's going to happen when we multiply by the minus x squared? First term, we'll have a minus x squared over 2. And so I'm lining up the corresponding powers of x. The next term will be a minus x cubed over 2. Minus x to the 4th over 2. Wait, where are we at? X cubed over 2, x cubed to the 4th over 2 times 2. And then minus x to the 5th, 2 times 3 factorial. I'm not going to simplify these denominators just yet. I think we'll probably have to eventually. Don't want to simplify them just yet, because sometimes when you're doing the additions and subtractions, you can get patterns out of these. But unfortunately, since these denominators aren't going to be the same, we are going to have to actually compute those. So what's our last term? We want to do one more. So we will have negative x squared over 2 times x to the 4th over 4 factorial. That'll give us a minus x to the 6th over 2 times 4 factorial. So that was our x squared term. Let's do one more and move on to the x to the 4th. What's going to happen with our x to the 4th times everything? The first term is going to be this x to the 4th over 4 factorial, positive. So everything will be positive in this row. And then the next term, x to the 4th over 4 factorial times x will give us x to the 5th over 4 factorial. And then we will have an x to the 6th over 2 times 4 factorial. That sum is going to keep going. So what we would want to do now is add up each of these. We're adding up each row. And so you can kind of see we've got this diagonal thing going. So that's going to keep going. But at least if we had to do one more, when I multiply this x to the 6th term by the top series, the lowest power we're going to start with is x to the 6th. So the next row would start down here at x to the 6th. Then the next row would start at x to the 8th. So at least what we're getting is that there's nothing else that's going to affect these beginning rows. So we start to have the development of a series here that perhaps we can deduce a pattern. So our first two terms, we want to add now the rows. Add down the columns. So we only have a 1 for our constant term and an x for the linear term. What's going on with the squared terms? Well, we're going to have a positive x squared over 2, and then we're actually going to have a negative x squared over 2 from that multiple. And there's no other combinations of these powers that are going to give us an x squared over 2. So we have 0 x squared. I'm going to keep that 0 in just as a placeholder. Now we move on to our cube term. We have x cubed over 3 factorial minus x cubed over 2 factorial. So that is, common denominator is going to be 6. So this is 3 over 6. This is 1 over 6. So 1 minus 3 gives us negative 2 over 6, or negative 1 over 3. And now the last term that we have written. So again, this next row, if we were to keep going with our sum, or keep going with our product, the next row would start at x to the 6th. So we'd start over here. So there's nothing below these two columns. So these two columns are complete. We can add up their sum. And let's see what we've got. So we've got a positive x to the 4th over 4 factorial, another x to the 4th over 4 factorial, minus x to the 4th over 4. So we know it's going to be x to the 4th. Let's work out the denominators. And let's just make a little space for some scratch work down here. So we had 1 over 4 factorial minus 1 over 4 plus 1 over 4 factorial are the coefficients that we're trying to combine. So how do we simplify this? We can write it as 1 over 4 factorial minus, this is going to be 3 times 2 over 4 factorial. So I'm just multiplying this term by 3 times 2 in the denominator times 1, if you want to include that one. So put a 3 times 2 in the numerator just to make the denominators the same. And so all in all, what are we left with? It looks like we've got 2 minus 6 over 4 factorial. So that's going to give us negative 4 over 4 factorial, or negative 1 over 3 factorial. Now we got to do the x to the 5th terms. So again, let's just do our scratch somewhere off to the side. On tests and quizzes, I think this last exam was a lot better, but if you have to do any sort of scratch work, include those pages. Even if you want to just pull out a separate page to keep it away from your solution and have scratch work on a separate page, make sure you're uploading that to Canvas, and maybe note if you did scratch work on like your nice solution, and you're like, if you're skipping steps on your solution, make a note and just say see scratch work on a different page, and that'll let the graders know that maybe not all of your work had been tagged with that problem or something, but we can at least then scroll through and try to find any extra scratch work. Or you can also just tag the scratch work, put when you're uploading it to Canvas or to Gradescope, put your solution as the first page for that problem, and then put your scratch work, tag your scratch work for the second or third page. All right, our x to the 5th, we've got 1 over 5 factorial minus 1 over 2 times 3 factorial plus 1 over 4 factorial. So this one is not as nice, though factorials aren't too bad, especially since it's a product of all the lower terms. we can kind of see whatever we're missing. Finding a common denominator is fairly easy, which is a big reason why I wanted to keep them factored in factorial form. So this 5 factorial is going to contain everything in 4 factorial. We're just going to be missing this extra factor of 2. So let's write this as 2 over 2 times 5 factorial minus, here I've got a 2 and a 3 factorial, so I need a 4 and a 5. So 5 factorial is going to be 5 times 4, which will cancel those, and then 3 factorial. Plus, now 4 factorial, we're just going to need a 2 and a 5. So a 2 times 5 factorial. Our denominators are all the same, and now we've got 2 minus 20 plus 10. So 2 minus 10 is going to give us negative 8 over 5 factorial. And then the question is, do we want to simplify that at all? I don't think we want to. Always a debate is what is simplified and what counts as simplified. Of course, 8 we could factor into 2 times 4 and cancel out a factor of 2 and a factor of 4 from the 5 factorial notation. Though we also have to ask, is that going to help us? Is that going to make our work simpler? And I don't think it will. I kind of like having this factorial in the denominator, especially since it's corresponding to our x to the 5. Let's go ahead and write this as minus 8.
So was it not still a 2 times 5 factorial?
5 factorial. Usually if your numerator and or denominator, right, if we can write the denominator in terms of a known function, 3 factorial, 5 factorial, maybe the 6 and the 7 will have 6 factorial, 7 factorial in the denominators. That's usually a better way to write it in terms of working towards a closed form expression. Unfortunately, it looks like the patterns in the numerators not following a very nice pattern. We start with 2 positive terms, and then a 0, and then 3 negative terms. And I don't know if it's going to get any nicer than that.
Isn't it 2 times 5 factorial?
Does that make sense? Did I make any mistakes? Sorry, I'm just catching up, seeing a comment in the chat. Isn't it 2 times 5 factorial? What's 2 times 5 factorial? Let me check my algebra here. We've got 1 over 5 factorial, 2 times 3 factorial, 4 factorial. So we did 2 over 2 times 5, 2 times 3. We wrote as 4 times 5, 5 factorial, kept that factor of 2. Added a factor of 2, added a factor of 5. I think that's right. I don't think I made any algebra arithmetic mistakes there. So unfortunately, there's not quite a nice pattern like that's appearing between the numerators and denominators, right? We can't write the sequence of coefficients nicely. We've got 1, 1, 0, minus 1/3, minus 1 over 3 factorial, minus 8 over 5 factorial. Maybe if we compute a few more terms, there might be a nicer pattern that develops in the higher order terms, but it would be hard to deduce. So problems like this might just say something like write out the first 4 terms, write out the first 5 terms, and then you would essentially just leave your answer like this. And then the other thing we can do is take quotients. So if you were not having fun with that one, guess how much fun you're not going to have with these ones. We all love math and love science, but you know what? Sometimes it's a pain. It's what we got to do. So if we want to do sine of x equal or tangent of x, which is sine of x over cosine of x, we now need to divide our Taylor series So let's write them all out. And now let's see. So sine is going to be x minus x squared over 2 factorial plus x to the 4th over 4. And I just switched. It's the odd power. Sine is an odd function. So we need 3 factorial. This one should be 5 over 5 factorial minus x to the 7 over 7 factorial plus x to the 9 over 9 factorial minus, keep going. You're going to divide that by 1 minus x squared over 2 plus x to the 4th over 4 factorial minus x to the 6 over 6 factorial plus x to the 8 over 8 factorial. I didn't line up the powers of x in this case because we're actually going to have to rewrite it. So again, just like you learned in elementary school, we're going to do division the same way you would do the division algorithm for very large numbers. Where now, instead of a decimal-based system, we are using an x-based system, where our powers of x correspond to our placeholders. So how do we do that? Well, we get a lot of space on our paper, and we need to take the numerator divided by the denominator. So we want to see how many times the denominator goes into the numerator. We are going to write our denominator on the outside. So let's see, where do we want to space this? This should be enough. Let's write 1 minus x squared over 2 plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial. And we want to divide into, I might have included too many terms, because here you want to keep spaces for everything if you need to. Let's start with x, and then let's keep a little space, minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and then minus x to the 7th over 7 factorial. That should be enough. So typically when you're doing polynomial long division, you want the process to terminate. And if you want the process to terminate, you usually start with the highest powers and work down. The problem is, of course, since we don't have highest powers, since they're infinitely long, the only other way to do it is to start with the lowest powers and then work up, which will give us an infinite series. So, of course, if we did want to find the correct power series, we would have to do this algorithm an infinite number of times. So usually the problems simply ask to find the first 3-4 terms of the series. So what we're going to do is look at the lowest powers, and we want to know how many times does 1 go into x. It goes into x number of times. And so now what we do is we take our x and we multiply by the entire polynomial. And what are we going to get? We are going to get x minus x cubed over 2 plus x to the 5th over 4 factorial minus x to the 7th over 6 factorial. So in this case, I guess we didn't need to space things out because nicely enough, since cosine and sine are just alternating, or I guess degree 2, or a sequence of even and odd terms, that we might actually see that our division might skip some of those terms as well. And so what we want to do is, after we take our product of this term times that one, we then subtract that off from our numerator. So the x's, of course, will cancel, and now we've got to do all of the factorial arithmetic, all of the coefficient arithmetic for each of these powers. So what is this going to be? This is going to be negative. Do some scratch work. Let me see if I can try to get it on the page for our x cubed. We're going to have a negative 1 over 3 factorial plus 1 over 2. So, of course, that's going to give us 1 over 3 factorial, sorry, negative, plus 3 over 3 factorial, which gives us 2 over 3 factorial. So here we will have 2x cubed over 3 factorial. Here we will have a 5 factorial, 1 over 5 factorial minus 1 over 4 factorial. And after we do a few of these, maybe we'll see a pattern. So 1 over 5 factorial minus 5 over 5 factorial is going to give us 4 over 5 factorial. And let's see. Let's make sure we got the sign correct. That's going to be a negative 4, yeah. So we'll have a minus 4x to the 5th over 5 factorial. And then here, what are we going to have? We're going to have 1 over 7 factorial negative 1 over 7 factorial plus 1 over 6 factorial, which is 7 over 7 factorial. So we're going to get 6 over 7 factorial. So saw a pattern here with some of these factorial coefficients. We could come up with this row now. However, now we have to repeat the algorithm. So unfortunately, those aren't the coefficients for our series. We now have to move on to this expression here. And so how do we get this term? Now we are looking at how many times our 1 is going to go into this expression here. So I think the book and other sources often simplify these just so you keep a list of the constants. Like they write this as whatever, I think it'd just end up being 1/3 here. Let's keep it as 2 over 3 factorial and see if we can get a pattern to emerge with the numerators and denominators. So what are we going to need? 1 going into 2 over 3 factorial x cubed. We are going to need the 2 over 3 factorial and then 2 powers of x. So this is where maybe lining things up would help, since this isn't necessarily over the x squared column. Let's just make sure we're keeping track of everything, and then we repeat it. So we take this term and multiply by everything. That's going to give us a 2x cubed over 3 factorial minus 2x to the 4, or x to the 4th over 3 factorial. And unfortunately, now it looks like we do need some of that space. So we will have x to the 4th over 4 factorial So those 2's there divided. X to the 4th over 3 factorial, yeah? Did I miss that? Yeah, 3 factorial. I'm looking at the next term there. Then our x squared times x to the 4th is actually going to give us 2x to the 6th over 3 factorial times 4 factorial. And that term's going to be positive. Did I miss something? Wait a second. What did I do? 1 times x cubed. What did I? Oh, sorry. I'm brain fart. Sometimes my eyes wander in when I look at the different digits. So, of course, this one we need an x cubed. Why did I write an x squared there? And this is the perils of doing long arithmetic. The probability of making one little mistake of a little brain fart, either with a minus sign or looking at a different number while you're trying to write, and then your brain writes that number instead of what you were trying to accomplish. So we had a 2x cubed over 3 factorial. So we need 1 going into that. We need 2 over 3 factorial x cubed. Let's erase this row and just try to line things up now, because these should cancel. We have a 2x cubed over 3 factorial. Now we take 2 over 3 factorial x cubed times this guy will give us x to the 5th over 3 factorial. And that term will be negative. And then our next term is going to give us x to the 7th, 2 divided by 4 factorial, 3 factorial. And that term's going to be positive. So a lot of this, we're really just minding all the bookkeeping, all of the positions, all of the minus signs, the coefficients, the degrees of x. Mind all of that. And so what do we get? We're going to want to subtract off all of these guys. So that one's going to subtract off and give us 0. What's going to remain here? Let's pull up some scratch paper. Let me try to get this all on screen here, just while we work out these coefficients. So we've got 4 over 5 factorial, negative. This term will be positive 1 over 3 factorial. And so doing the algebra on that, we've got minus 4 over 5 factorial plus 5 times 4 over 5 factorial. And let's see, is that going to be nice? Not quite. 16 over 5 factorial. So that'll be our coefficient here. Positive 16 over 5 factorial, x to the 5th. And then this one here, we've got 6 over 7 factorial minus 2 over 3 factorial, 4 factorial. Now we're getting into stuff that's not so nice, especially when we have products of factorials. So how can we simplify this? Well, the 4 factorial is closest to the 7. So let's write this as 6 over 7 factorial. We might modify this term still, so let's leave some space. This is going to be 2 times 7 times 6 times 5 over 7 factorial. That was the 4 factorial, and then we still have this 3 factorial. So 7 times 6 times 5 would cancel those terms out of the 7 factorial and give us back that 4. So we are closer to a common denominator. Now I need this 3 factorial. That is one way we could do it. Of course, we could even try to simplify this and write 7 factorial, cancel out the 6. We could cancel out the 2 from one of those terms, and then try to simplify it from there if you'd like. Unfortunately, it doesn't look like, especially once you have products of factorials, it doesn't look like it's going to be terribly easy. Any way you do it. So what do we got? 6 times 3 times 2 minus 7 times 6 times 5 times 2 all over 7 factorial times 3 factorial. And let's see, do we want to multiply those numbers out, or do we want to divide and cancel? I think at this point, with the complication of the numbers involved, we are going to go ahead and abandon this factorial notation since our numerators are getting more complicated. And since we have to multiply everything out, let's go ahead and make it look how it would look if we abandoned our factorials from the get-go. So we've got a 6 and 2 from everything. That'll give us a 3 minus 7 times 5 over 7 times 6 times 5 factorial, and then times 3 times 2 for that 3 factorial. So that 6 will cancel, that 2 will cancel. Our numerator, we've got 3 minus 7 times 5, so 3 minus 35 gives us negative 32. And then in the denominator, I'm getting 7 times 3 is 21 times 5 factorial. So whatever that is, 5 factorial is what, 600 or something like that? Is it 120? So 4 factorial is 4 times 3 times 2. So 24. So 5 factorial is 120. And when the numbers get this bad, personally, I think it's fine to just leave it as products. I think products of 2 digits times 2 digits, typically, you can do those fairly quickly. If it's a 1-digit number times a 2-digit number, you can do those fairly quickly. As soon as you get to 2 digits times 3 digits, I'm going to leave it as 21 times 120. So this digit here was negative, or this coefficient, 32 over 21 times 120. X to the 7 is what we had there. So let's take a step back. This is the problem with doing algorithms. And those of you in computer science will run into these type of issues a lot. If you haven't already been kind of running into these with a lot of these more complex calc problems, you get into one chain of work and then have to break it down into a smaller problem of adding coefficients, and you can lose sight of where you were at. So what we were doing was just simply simplifying the coefficients. So to reassess where we were at, we got rid of this x cubed term, and now we found the coefficients for the x to the 5th and the x to the 7th term that remain. The next step in the algorithm would be now to look at how many times does 1 go into our remaining x to the 5th term. So there we would have a plus 16 over 5 factorial x to the 5th. Next step of the algorithm would be to take that 16 over 5 factorial x to the 5th, multiply it through by everything. So of course the first term will give us 16 over 5 factorial x to the 5th, but then we will have a minus 16 over 5 factorial times negative 1/2 over 2, and then x to the 7th. And then we would get the joy of doing this process again, which I am not going to go through. So of course the x to the fifths are going to go away. If you want to continue on to x to the sevenths, be my guest. But at least for this, we have computed the first 3 terms of tangent of x. So let's go ahead and write that out a little more nicely somewhere. So I'm going to put the scratch work. I'm just going to throw that page away. And so we've got tangent of x. It's going to be x plus 2 over 3 factorial x cubed plus 16 over 5 factorial x to the 5th plus some higher order terms that get really complicated. And if we wanted to simplify or at least change how the coefficients look a little bit, we can write this as 1/3 x cubed. 16 is 4 times 4. So this is going to give us 4 over 5 times 3 times 2, which is going to give us 30. X to the 5th. And of course, that one can even be simplified one more time. So we get something like that. Unfortunately, hard to see a pattern just yet. If we wanted to find a pattern for the coefficients, maybe we would want to compute out that x to the 7th term, simplify all the fractions and see what we get. Patterns going 1, 1, 2. Maybe the next term could be a 3 factorial. We've got 0, 3, 15. There might be a pattern developing in the denominator. So if you want to find the actual series, the actual Taylor series for tangent of x, go ahead, look it up in the book or look it up online. Pretty easy Google search will probably bring it up. And then try to see if you can match the closed form expression of the coefficients with your work in the division algorithm. Any questions? All right, let's take a break. That is a good point to take a break, flush our brains. We were just doing some hard calculations. Unfortunately, I hate getting into the hard calculations because it kind of can eat up at your brain power quite a bit. And unfortunately, I hope the process made sense, but in my opinion, I don't think anyone learned a whole lot. Like if you know how to divide numbers and you know how to divide polynomial long division, you probably didn't learn a whole lot from this other than the fact that these coefficients and now just power series, Taylor series in general are a big pain. And that if we were to try to do this, it would be best to develop a computer algorithm. Much better to write a computer algorithm to try to divide power series, which I would highly encourage all you guys to do, especially as you get higher into your computer science classes, if any of you guys have to take that, to try to work on polynomial algebra within computer systems is a good skill to develop, good thing to understand. But we do want to finish off the day. We want to talk about Taylor's remainder theorem. That gets into a little more math. Again, it's kind of one of these application topics. So like the math and the theory behind it isn't terribly interesting. It is kind of more of an application-based problem where we are doing some more computational-based approaches and computational-based problems that we're trying to solve with that. So let's take a break, and then we will take a look at that in the last 20 minutes of class or so. Go ahead and start recording again. I forgot there's a couple of announcements just in terms of the exam. So exam grades are posted for exam 3. We haven't posted the solutions yet. So you can wait if you want to see the solutions, but if you want to look over your exams on Gradescope, feel free to do so and send me any grade disputes. One student already has. So I was able to get back to them. And then once we're finished handling all the grade disputes and the regrades for exam 3, we need to then update Canvas. So I think all of the exam 1 scores, any exam 1 grade disputes, exam 2 grade disputes, and then exam grade 3 grade disputes. Once all those are kind of set, I think we can then update all of the grades in Canvas to reflect your Gradescope grades. So if you've had grade disputes and we've given you points back on anything, Gradescope scores should be accurate. I don't know if they've been updated in Canvas yet, though. So we'll get to that probably this week, if not today or tomorrow. All right, so we got 20 minutes. And we need to talk about the remainder theorem for Taylor polynomials. So let's go ahead and take a look at that. Let's go ahead and get a new sheet of paper. So if Tn of x is the nth degree Taylor polynomial, for f of x at x equals a. So we mentioned a little bit when I introduced these concept of Taylor series and power series that another way you can interpret Taylor series and power series as approximations to functions, to differentiable functions. In Calc 1, you saw linear approximations. Those were kind of hidden in the concepts of tangent lines, that whenever we're actually finding a tangent point line to a curve or to a function at a given point, really that is the first order approximation. The equation for that tangent line would be the Taylor polynomial of degree 1. And we were talking about how, well, what if we wanted to be more accurate? If we wanted to represent a function, I mean, a function's not going to be a straight line, so maybe we could be more accurate in approximating the function with a quadratic or even a cubic term. And through that process, essentially what we derived was the Taylor series. That the Taylor series really is the infinite degree polynomial expression, approximation to the function. And so if we want an approximation to the function, and we know the power series or the Taylor series, we can essentially just stop the Taylor series at a given value of n. And the book uses lowercase n. I think it might be better if we used capital N. Since lowercase n is used as the index of the series, let's use capital N as the stopping point, the maximum number of terms or the maximum degree of x is what this capital N is going to be. So we're just taking an nth degree polynomial. So we're taking capital N terms. Then we define the remainder which you can really think of as the error as f of x minus this polynomial. In other words, if f of x has a well-defined Taylor series of infinite degree, f of x is going to be this guy minus the Taylor series, which just goes up to degree n, And I forgot my power of n there. And so here, let's actually put our notation here. So the remainder is just denoted Rn of x. Which, after we subtract those series, we are just going to get something that looks very similar, except we're just going to start at the n plus first term and go up to infinity. Now, this doesn't quite help much if we want to bound the remainder because we still have an infinite series. So there is a theorem and this is Taylor's remainder theorem. I actually don't know if it's named after Taylor, since a lot of those guys during that time, a lot of the mathematicians, used each other's work and then built on it, and then some of them wrote their own books using some other people's work. And even though I'm sure it's credited, I think it might be Laplace who might have been the first to come up with this. But anyway, as part of Taylor's remainder theorem and Taylor's theorem for polynomials and Taylor's series, we have that the bound. So how much do I want to write out? Let's just write out the whole thing. So for Tn of x, the nth degree Taylor polynomial for f of x at x equals a with interval I, potentially, including the bounds of the endpoints. Then for any x in that interval, so that x element of I just means we have an x value between a and b, there exists a special x value, which we're actually going to call z, between the center and this x value, such that the remainder is equal to, and let's use capital N, excuse me, is equal to this guy. So take a look. Notice that this looks very similar to the starting term here. The only difference is we are not evaluating the derivative at this base point. So that's essentially what it's saying. It is saying that the remainder in a Taylor series is essentially related to that order of derivative, or the next order of derivative. So our nth remainder is going to be related to the n plus first term of the Taylor series, except the only difference is we are really going to be looking for a bound, a special z value that will maximize the n plus first derivative. So, example. Go ahead and write our theorem here at the top, or at least write our formula, just to have it handy on this page. Example, approximate f of x equal to cube root of x at x equals 8 by a Taylor polynomial of degree 2. So that's going to be A, and then B, we want to know how accurate is this Taylor polynomial when x is between 7 and 9. So we've got to go through the process now. So this is kind of the caveat of Taylor polynomials. It's nice to know all of your well-known power series and Taylor series, but now if we want to approximate functions at different base points, we're going to actually have to go through the process. If we were to try to come up with a Taylor series for x cubed or x to the 1/3 at x equals 0, well, I guess we'd have to go through that exact same process. We could try to finagle it with the binomial coefficient power series that we derived yesterday, but that might be just as difficult. But of course, even if it's a polynomial or some other nicely well-known function, unfortunately, if we change the base point, we've got to go through the process. So best way to do these is to, again, make a table, f of x, cube root of x, f prime of x is 1/3, x to the minus 2/3. So I'm just going to switch to fractional exponents, going to make our lives a bit easier. So we'll have minus 2/3 squared, x to the negative 5/3. Our third derivative, never mind. We can stop there. Since we only wanted degree 2, we only need to go down to derivatives of order 2. And so we can evaluate those at x equals 2, x equals 8, excuse me. And what are we going to get? F of 8 is 2. F prime of 8 is 1/3 times, let's write it as 1/8 to the 2/3. So that's going to be 1/3. 8 to the 2/3 is 4 squared. I always do the roots first. Anytime you have fractional exponents that you're evaluating, do the roots first, especially if you can. So 8 to the 1/3 is 2, then square it, gives us 2. So that'll give us 12. And then f double prime of 8 we'll do similarly. So we've got minus 2/3 squared times 1/8 to the 5/3. And again, easier to make it smaller first. So that's going to be 2 to the 5th, which is 32. So minus 2/3 squared times 32. Unfortunately, not going to simplify too much. So minus 2/9 times 16. And still a little hard, but again, 2-digit numbers, not terrible. So that's just 90 and 54. So 144. And then I guess that can be simplified with, wait a second, did I forget this power of 2? 8 to the 5/3 was 32. Yeah, sorry, I already got rid of that power of 2. 1/144. Yeah, so that power of 2 canceled with the 32 to get the 16. I just rewrote it accidentally. And that was a negative. So our Taylor series, or Taylor polynomial of degree 2 of x, following our formula, f of 0 plus f prime of 0 over 1. sorry, x minus 8 to the 1 plus f double prime of 0 over 2 x minus 8 squared. We can fill in our values. And we are going to get f of 0 was 882, sorry, plus 1/12 times x minus 8. And then now we're going to have an extra factor of 2 on this guy. So this was negative 1 over 288 times x minus 8 squared. And then now for the last bit, just sorry, we are a little bit out of time, but let's go through that real quick. So here's our Taylor polynomial. We are going to have to compute the next term because of the remainder theorem. It has to deal with the third derivative. So if we want to know how accurate it is, we would compute our third derivative, f triple prime of x. So we had minus 2 over 3 squared. Now we're going to have times a negative 5/3. So that's going to be 2 times 5 over 3 cubed, x to the negative 8/3. Which, unfortunately, those numbers are not going to simplify too easily. Nothing cancels. And so what we want, let's go ahead and rewrite our remainder theorem. And let's actually fill in the values here. So our remainder of 2 for our degree 2 Taylor series is going to be the third derivative evaluated at some special point over 3 factorial x minus 8 cubed. And now we know that the third derivative evaluated at z, we're just going to have a z value there. So we will have, let's go ahead and write everything out, 10 over 27. We've got an x to the 8/3. Let's go ahead and put that in the denominator. And then this 1 over 3 factorial will also be in the denominator. Times, and this, sorry, should have been a z. Be careful with this. Sorry, let me write that cleaner since the pen isn't so clear. So we had 10 over 27. We had a z to the 8/3. Remember, we want to evaluate f triple prime at some arbitrary z, or I guess I shouldn't say it's not an arbitrary z, it's a special choice of z that we'll work with in a second and try to find the bound. This term here is still our x value. So we've got a couple of variables there, and then we had our 3 factorial here. And so simplifying a little bit, 3 is 3 times 2, 3 factorial, 3 times 2, so it'll cancel out factor of 2 out of that 10, and then we'll have 3 times 27 is 81. So this is going to be our expression for the remainder of the degree 2 polynomial. And we want to bound this, i.e., we want to find a maximum on 7 to 9. So, of course, whenever x is between 7 and 9. So the two things we need to do is, one, find the maximum z value, and then also bound this expression here. So since we have z to the 8/3, so essentially pick z and x in the interval to maximize. So whichever z and x combination maximizes this will be our answer. And moreover, I guess we should say we are looking for the absolute value of everything. So we're looking for a positive error, a positive bound on the error in the remainder. So how do we do that? We note that, of course, 7 to the 8/3 is going to be less than or equal to z is going to be less than or equal to 9 to the 8/3, z to the 8/3. So that's our expression for z in the denominator. And as z increases, the entire expression is going to increase, meaning that if we want to maximize the denominator, since the z to the 8/3, we actually pick z equal to 7. So 1 over 7 to the 8/3 is going to be maximized. Likewise, for x, since x is between 7 to 9, we know that the distance of x minus 8 cubed in absolute value, the maximum it's going to get is 1. So whether I pick 7 or 9 for that expression, it's always going to be at most 1. So what we're going to do is replace this expression. We're going to pick 9 for our x, and we're going to pick 7 for our z. So the overall bound for the absolute value of our remainder is going to be 5 over 81 times 7 to the 8/3. So we picked our smallest denominator there to maximize that overall expression, times absolute value of 1 cubed. And these ones, usually when you're finding error bounds, you are looking for a decimal approximation. So I think the book calculates this. It ends up being, I want to say something like 3 zeros and then a 4 on the 4th zero. So compute that out to get a reasonable decimal of how accurate this Taylor polynomial is on that range. Any questions?